Okay, so this is just chapter 16 homework and number 1, where we have the motion of a 2.5 kilogram rod with an applied force of 8 newtons, and we're supposed to find the acceleration of the rod and the reactions at A and B. So to find the acceleration, we could just equate the forces in the x direction and then solve for the acceleration, which is 3.2 meters per second. After that, we can equate the system of external forces with the system of effective forces. And by doing that, we come up with mg times r minus 2r over pi minus ar is equal to ma times 2r over pi. And then solving that equation for A and plugging in our knowns, we get 3.82 newtons for the reaction at A. And after that, we can sum the forces in the y direction and solve for 20.7 newtons on the B, for the reaction point at B. Number 2, we have a triangular weldment that's connected to 2 different slots, and the velocity at each pin is 30 inches per second. We're supposed to determine the acceleration of the weldment and the reaction at A and B. So first of all, we can determine the acceleration in the normal direction, which is 30 squared over 6, which is like 12.5 feet per second squared. And then using mg cosine 30 is equal to ma in the tangent direction, we can solve for the acceleration in the tangent direction, which is 27.89 feet per second squared at 60 degrees. And we know that the total acceleration is equal to the tangent acceleration plus the normal acceleration, both squared, and taking the square root of that. So we'll get 30.56 feet. And if we do some trig, we can find out that it's at 84.1 degrees. And doing that, we can solve for ma, or the force, and we'll get 15.18 pounds. And then we can equate the system of external forces and effective forces at A. And from that, we can solve the reaction point at B. And once we have the reaction point at B, then we can just equate the forces in the x direction and then solve for A. Okay, number 3. We have 2 wheels that are brought together applying a force of 20 newtons. And we're supposed to determine the angular acceleration of each disk and the final angular velocity of each disk. So first we can find the inertia at A, and then we know that the force when they're coming together is mu times normal, which is 0.5 times 20, it's just 3 newtons. So we know the inertia at A and the force of 3 newtons. Then we can equate the moment at A and the moment at A effective force and external forces. In doing that, we can solve for the angular acceleration, which is 12.5, and we can also find the inertia at point B, which is 0.004 kilogram times meter squared. After we do that, we can also equate the system of external forces to the system of effective forces at point B. Doing so will give us the acceleration of the angular acceleration of B, which is 33.3 radians per second. And we know that the disk will stop when VC is equal to VD. Using that, we can come up with the relation that the angular velocity times the radius of A is equal to the angular velocity times the radius of B. And plugging in, we can solve for t, which is about 1 second. And then from that, we can solve for the angular velocity at A and the angular velocity at B, which is 240 RPM and 320 RPM respectively. Okay. Number 4, we have a drum that's attached to a disc, and they have a combined mass of 5 kilograms, and they're suspended by 2 cords, and we are supposed to determine the combined radius of gyration of the disc in the drum. So we know that I is equal to mk squared, and we can just plug in our knowns there and get I is equal to 5k squared. And if we sum the forces in the y, we can solve TA plus TB minus the weight is equal to MA. We can solve for our acceleration from that equation. We know that acceleration is equal to the radius times the angular acceleration, which will give us our angular acceleration of about 10.95 radians per second squared. We also know that sum of the moment at point G is equal to the inertia times the radial acceleration. So from that we can get TA times RA minus TB times RB is equal to I times alpha, which will give us our K being 170.95 millimeters. Number 5. Number 5, we have a uniform slender rod of length L and a mass of 4 kilograms. It's suspended from a hinge. We're supposed to determine the angular acceleration of the rod and the components of the reaction at C. So first we can equate the system of external forces to the system of effective forces. And we know that I is equal to 1/12 times ml squared, and A is equal to R alpha. Using those and the equated forces, we can then come up with this equation on the right hand after combining them. And we can plug in our knowns to that equation and solve for the angular acceleration, which is 107.14 radians per second. We know that Cy minus the weight is equal to 0, so we can solve for Cy using that equation. And then we know that Cx minus the force is equal to the weight, to negative of the weight. And using that equation, we can solve for Cx. All right, number 6. We have a wheel with a centroidal radius of gyration k that is released on an incline and rolls without sliding. We're supposed to determine an expression for the acceleration of the center of the wheel in terms of R, K, B, and G. So all we really need to do is equate the system of external forces with the system of effective forces at point C, knowing that I times alpha is equal to mk squared times alpha, and ma is equal to mr alpha. And using the equated forces, which is rmg sine of beta is equal to ma times r plus I alpha. And combining all three of those equations, we can solve for our alpha. And then after we solve for alpha, we can use the relation of alpha is equal to r times a, and we can get the actual acceleration at the point. Number 7. We have a drum that's attached to a disc and is pulled with a force of 5 pounds. We're supposed to determine whether or not the disc slides and the angular acceleration of the disc and the acceleration of g. So we know the relation acceleration is equal to r times alpha. So a is equal to 8 over 12 times alpha, and then we'll save that for later. We know that I is equal to mk squared, so we can plug in our knowns here, and we can solve for the inertia, which is 0.0774 slug feet per second squared. And then we can equate a system of external forces with a system of effective forces, and get this equation here, which we can use to solve for the angular acceleration, which is 7.73 radians per second. And again, we know that acceleration is equal to r times the radial acceleration. We can plug in our knowns, solve for a. Then we can just sum the forces in the x direction, and we get a force of 1.6 pounds. We can sum the forces in the y direction, and we can solve for a force of 1.25 pounds. And we know, since F is greater than Fm, that the disk must slide. So now we can solve with the kinetic force, kinetic mu, and get 1 pound, about 1 pound. And then we can equate the system of external forces to the system of effective forces for point G. And then plugging in our knowns, we can solve for the radial acceleration, which is 12.88 radians per second. And then we can just sum the forces in the x, and then solve for the actual acceleration, which is 3.22 feet per second squared. Okay, number 8. We have 2 uniform discs, each of a mass 2 kilograms, and they're connected by a 2.5 kilogram rod. A moment of 2.25 Newton meters is applied to disc A. And knowing that the discs roll without sliding, we're supposed to determine the acceleration of the center of each disc and the horizontal component of the force exerted on the disc by pin D. So we can solve for the inertia of each circle, each disc, with this top equation here. I is equal to mr squared divided by 2. So the inertia for each disk is 0.0225 kilogram meters squared. Next, we can equate the system of external forces with the system of effective forces. And we can solve for Cx using this equation. And then we can do the same thing, but at point Q instead of point P, and solve for dx. Then we can sum the forces in the x, which is Cx plus dx is equal to mcd times 1 plus t over r times A. Plugging in for cx and dx, we get this long mess of an equation which simplifies down into m is equal to 2 times mr plus I over r times A plus mcd times A times 1 plus b over r times r plus b. And plugging in our knowns there and solving for A, we get 1.9231 meters per second squared.